are going to go over electric charge and electric force. This should be the very first lesson of E&M, so welcome back. Okay, so to begin, we are going to be looking at forces and charges, but before we go there, as a quick reminder, from mechanics, we learned that force is equal to mass times acceleration. Now, we will be using this formula once again in E&M, but the reason why I'm bringing this up is because on your formula sheet, you have a chart of givens and known quantities. And so the thing I want to point out is the masses that we will be using for E&M. So I'm going to go ahead and highlight them. And if you just want to quickly just pause the video and jot down these quantities so that you have it. Now, it is on your formula sheet, but more of a quick reference so that you can have it in the future. So the first one is the proton mass of 1.67 times 10 to the negative 27 kilogram. The neutron mass, which is the same in magnitude. Now, if you remember chemistry, that is true in chemistry as it is in here. Protons and neutrons have the same mass, but if we take a look here, the electron, which is a lot smaller, is 9.11 times 10 to the negative 31st kilograms. The next thing that we're going to be using a lot is this electron charge magnitude. Okay, so now is a good time to remind ourselves the word magnitude means that there is no signage, it is just the numerical size of the charge. And the magnitude for all electrons is 1.6 times 10 to the negative 19. We'll be using that one a lot. All right, and the other one that will pop up later, but I'm going to point it out now, is this epsilon naught right there. Okay, that epsilon naught is going to be 8.85 times 10 to the negative 12, but I will, of course, point your direction in this. Coulomb's law constant, which can be rewritten as a k, 1 over 4 pi epsilon naught. So if you take a look here, we see that's where the k is, and so you'll see me write f of e as k q1 q2 all over r squared. It's just a lot quicker to write than 1 over 4 pi epsilon naught. However, this is the official form, and a lot of the problems actually revolve you understanding and manipulating the formula in that form. All right? All right, so with that out of the way, let's go over the basics of the atomic model. All right, so we have an atom, and inside the atom, we have what we call neutrons and protons. So let's just draw one N and one P there. And orbiting the atom, we have what we call an electron, right? So this is, of course, not to scale. You know that the neutron and the protons are way bigger than the electron, so that is definitely not to scale. But just to show you that inside the atom, we have the neutron and the proton, and outside is the electron. And this inside part of the atom, we call the nucleus, and we often say that the electron is orbiting around the nucleus. All right, so in terms of, for this class, how you'll see me, I guess, write and draw the different parts of the atom, okay? So with anything that is neutral, you'll just see me write it as a equal sign. With anything that is a positive charge or a proton, you'll see me write it as a plus. And whenever you see me deal anything with electrons or negative charge, you'll see me write it as a negative. So with that same model, we can easily redraw it like so. Okay, so the reason why this is important is because with E&M, a lot of the times we communicate through images and figures. So if I were to show you a image that looks something like this. Okay, so what we can see here is whatever object, it's a rectangular of some sorts. We see that the negative side of the object is on the right, and the positive side of the object is on the left. Okay, so another rule of for this course is we often draw things when it has a net charge. All right, so this is one of those words that we used a lot last year, but just as a reminder, net just means like the overall summation. So for example, let's say we have a system, and in the system we have 1, 2, 3, 4, 5 positive charges and 1, 2, 3 negative charges. So in a case like this, it's a little bit more cumbersome to constantly draw all those 5 positive charges and those 3 negative charges. So a easier way of representing this is to just either draw the overall net charge. So we have 5 positive and we have 3 negative. So the net would be 2 positive. So we would just draw it like this. Or we could represent the object as either just 2 positives or plus 2. And what should I do here? The lowercase q. So q is the variable for charges. Okay. All right. Now let's go back to the chart because that's going to help us out with a little bit more discussions. Okay, so we discussed that Q represents the amount of charge or net charge that could be represented on an object, and the units for charges is this, capital C, and that capital C is for coulombs. All right, so let's just write this here. This is for charge or net charge, and the units is capital C, and this represents coulombs. Okay, and that's the scientist that did a lot of studying for the static electricity. All right. So let's just do one more example of net charge, just so that we have a good foundation for this. Let's say we have 1, 2, 3, 4, 5, 6, 7, 8. All right. Okay, so if this is our system, we can see that in this system we have a total of positive 3 coulombs, and we have 1, 2, 3, 4, 5, 6, 7, 8 negative coulombs, or negative 8 charges. So the net charge, we would just simply redraw this as negative 5q. All right, so it's always helpful to write it in the 1, 2, 3, 4, 5 in the net view, okay, not the all the components that make it up. All right, now with that, let's go into the law of charges. All right, so you might have heard this before, but the idea behind two charges being close to each other, and we should have explored this on the first day back, is that when you have charged objects near each other, they exert a force, and this is where Coulomb's law comes into play. So Coulomb's law, named after, well, the physicist that was exploring this, Coulomb, and also the same as the unit, his formula is F of subscript E, Coulomb's constant, Q1, Q2 over R squared. It's the same formula I showed you before, but this is going to be the version that I read a lot. So what this tells you is that if you have two systems of charges and they are separated by a distance, okay, and that distance we just call R, they will exert a force on each other. Okay, so the force, I think, is a good time to remind ourselves there's two ways that objects can experience a force. This force can be either a push or it could be a pull. So one of the other things that we can do is we could also combine this F of E, if it's the only force acting on the object, right? We can make this also equal to ma. All right. Now the Coulomb's law also has very specific points about what pushes and what pulls. So I'm going to write this down. Is repel, and unlike charges, attract. Okay, so let's just zoom in there. So what this means, let's do the like charges repel first. So the rule of thumb is if you have two systems that are both net positive, both of these will repel each other. Meaning, so I'm going to actually do this one in blue, and let's just do this one in green. So this, the one on the left, because it has a positive charge, it will feel a force from the positive charge on the right. And the direction of that will be to the left. Okay, so you see how this like charge is moving far away from the other like charge. And in reversal, the one on the right, because it has the same charge as the one on the left, it'll feel a repulsive force going to the right or away from the source of positive charge. Okay. Now, it's also important that Newton's laws still apply even in this tiny atomic scale. The third law applies, meaning that the magnitude of the force is identical to each other. And this is important because one of the ways that they'll try to trick you is, I'm going to choose a different color actually, is let's say you have a net charge of 500 positive coulombs, okay? And over here we have a total of positive 2 coulombs, okay? So even though the red one or the one on the left is so much more positive than the one on the right, it doesn't matter in terms of the amount of force. Okay, so the red one on the left will still be pushed away from the charge on the right with a certain amount of force, and the one on the right will feel the identical amount of force. Okay, so this will be Fe, and this will be Fe, and these are the same. Okay, and if this were the FRQ, you could always cite the third law. All right, so we just talked about positive charges, and the other one that is true is negative and negative. Now there is a caveat, right? And that is with neutral objects. So if you have a neutral object and a neutral object, because they're both not charged, they don't exert a force on each other. And the idea, right, is even in equation form, Q1, Q2 all over R squared. If you have a neutral object, that means that your Q for neutral, is going to be 0 coulombs. Okay, so if we put in 0 in any of that formula, the net force will become 0. Okay, so only charged objects. All right. Next, we have unlike charges and they attract. And of course, there's a little caveat with that as well. So let's just do a quick little example. We have a positive charge here and a negative charge here. Okay, this positive charge will be pulled towards, so I'm going to use my color system again. This will be red, and we'll make this one green. Okay, so this positive one will be pulled towards the negative charge, and this negative charge will be pulled towards the positive charge. Okay, and once again, the third law is still in effect. The amount of force will be identical. All right, now because those are the only combination of unlike charges, that's about it. Except there is actually like kind of corner cases. Okay, and this is with charged objects and neutral objects. So if you have a positive object here, and you have a neutral object here, and a negative object here, and a neutral object here, these systems will actually attract to each other. And the reason why actually comes up next in our unit, so I won't go into any detail here, but what this means is that this positive object will be attracted to the neutral object, and this neutral object will be attracted to the positive, and vice versa. Okay, there we go. So the rule of thumb is like charges repel, unlike charges attract. Now, because we're dealing with forces, just like in mechanics, the types of questions that you'll see will often include two dimensions. And so if it does include 2 dimensions, we have to make sure that we're looking at the net charge. So I'll just go through a couple of quick examples without any calculations. All right. So let's say we have a positive charge here, we have a negative charge here, and a negative charge here, right? And let's say the question says, what is the net force on this middle charge? Okay, so in order to do this, you have to first calculate how much this middle charge feels a force from this left one. So let's just make up some numbers. Let's say this middle one feels a pull to the left with a force of, let's say, 2 newtons to the left. So I'm going to make that negative. Okay. Now, also a quick little side note: when you do these problems, just like what I'm doing with those sketches, it really does help to sketch out the charges and the diagrams and the direction of the forces. Think of it just like, well, it is actually a free body diagram. All right, and let's say this negative charge on the right exerts a force on this negative charge in the middle. Let's say it goes to the left because like charges repel with a total of negative 5 newtons. Okay, so what that means is that this middle charge will feel a total force of negative 7 newtons to the left. Okay. All right. Now, it's also important that this is like a frozen moment of time because we know that if like time were to continue, the one in the middle would move towards the left or accelerate towards the left, and that amount of force would change according to Coulomb's law. All right. So another common thing that they might ask you to do is a system of like 3 charges, kind of like this. So we'll say this one is positive, positive. We'll just make it 3 positive charges like so. And let's say this top one exerts a force on this bottom one with a force of, I don't know, negative 4 newtons. And we can say that this charge over here exerts a force on this positive charge, let's say over here, negative 3 newtons. All right. Now, so the question would be, what would be net charge on this most bottom one? Okay, and then in this case, we have to use our favorite math formula, the Pythagorean theorem, and you would see that the net charge here would be 5 newtons. Okay, and we just use the Pythagorean theorem for that one. All right, so we'll see a lot more different kinds of problems, but those are the basics. And the only thing I did not show you in these examples is actually using Coulomb's law, which is right here. Okay, and that's just because all you got to do is plug in the values that the problem gives you. And just as a quick heads up, because we'll be using this k a lot, right? You'll just see me sometimes write it as 9 times 10 to the, what was it, positive 9, negative 9? I forgot. What is it? Positive 9. I can't believe I almost forgot that one. Positive 9. Okay, so you might just see me write that on the board as 9 times 10 to the 9. All right, that's it. I'll see you in class. Bye bye.